Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. This is a podcast where I read old books, sometimes fiction, sometimes non-fiction, in the most boring way I can, to try help slow your spinning mind enough for you to fall asleep in the most natural way possible. The stresses of life often follow us to bed and keep us company, but I'm here to distract you from them and help you drift away. Before you do fall asleep, if you find Sleepy Time Tales helpful and you would like to support me, to keep it going out to you and thousands of your fellow insomniacs, please consider signing up on the Patreon at patreon.com/sleepytimetales. If monthly support is a bit much to ask for, you can put a tip in the tip jar in the Ko-Fi. These are both linked in the show notes. Or if you want to support Sleepy Time Tales without doing so financially, you can by just telling people about it. If you know someone who's struggling to sleep, let them know where to find it. That's enough of that. Let's start learning about how land is formed in the ocean. Snuggle down, close your eyes, breathe deeply, and listen closely as I lead you down the path to sleep. Back again this week to the Elements of Geology by Harmon Norton. Chapter 8. Offshore and Deep-Sea Deposits. The longshore deposits which we have now studied are the exposed edge of a vast subaqueous sheet of waste which borders the continents and extends often for as much as 200 or 300 miles from land. Soundings show that offshore deposits are laid in belts parallel to the coast, the coarsest materials lying nearest to the land and the finest further out. The pebbles and gravel and the clean coarse sand of beaches give place to broad stretches of sand, which grows finer and finer until it is succeeded by sheets of mud. Clearly there is an offshore movement of waste by which it is sorted, the coarser being sooner dropped, and the finer being carried farther out. Offshore deposits. The debris torn by waves from rocky shores is far less in amount than the waste of the land brought down to the sea by rivers, being only 1/33 as great, according to a conservative estimate. Both mingle alongshore in all the forms in beach and bar that have been described, and both are together slowly carried out to sea. On the shelving ocean floor, waste is agitated by various movements of the unquiet water, by the undertow, an outward running bottom current near the shore, by the ebb and flow of tides, by ocean currents where they approach the land, and by waves and ground swells, whose effects are sometimes felt to a depth of 600 feet. By all these means the waste is slowly washed to and fro, and as it is further ground finer and finer, and its soluble parts are more and more dissolved, it drifts farther and farther out from land. It is by no steady and rapid movement that waste is swept from the shore to its final resting place. Day after day and century after century, the grains of sand and particles of mud are shifted to and fro, winnowed and spread in layers, which are destroyed and rebuilt again and again before they are buried safe from further disturbance. The processes which are hidden from the eye are among the most important of those with which our science has to do, for it is they which have given shape to by far the largest part of the stratified rocks of which the land is made. The continental delta. This fitting term has been recently suggested for the sheet of waste slowly accumulating along the borders of the continents. Within a narrow belt, which rarely exceeds 200 or 300 miles, except near the mouths of muddy rivers such as the Amazon and the Congo, nearly all the waste of the continent, whether worn from its surface by the weather, by streams, by glaciers, or by the wind, or from its edge by the chafing of the waves, comes at last to its final resting place. The agencies which spread the material of the continental delta grow more and more feeble as they pass into deeper and more quiet water away from shore. Coarse materials are therefore soon dropped along narrow belts near land. Gravels and coarse sands lie in the thick, wedge-shaped masses which thin out seaward rapidly, and give place to sheets of finer sand. Sea muds. Outermost of the sediments derived from the waste of the continents is a wide belt of mud. For fine clays settle so slowly, even in seawater, whose saltness causes them to sink much faster than they would in fresh water, that they are wafted far before they reach a bottom where they may remain undisturbed. Muds are also found near shore, carpeting the floors of estuaries and among stretches of sandy deposits and hollows where the more quiet water has permitted the finer salt to rest. Sea muds are commonly bluish and consolidate to bluish shales. The red coloring matter brought from land waste, iron oxide, is altered to other iron compounds by decomposing organic matter in the presence of seawater. Yellow and red muds occur where the amount of iron oxide in the silts brought down to the sea by rivers is too great to be reduced or decomposed by the organic matter present. Green muds and green sand owe their color to certain chemical changes which take place where waste from the land accumulates on the seafloor with extreme slowness. A greenish mineral called glauconite, a silicate of iron and alumina, is then formed. Such deposits, known as green sand, are now in process of making in several patches off the Atlantic coast, and are found on the coastal plain of New Jersey, among the offshore deposits of earlier geological ages. Organic deposits. Living creatures swarm along the shore and on the shallows out from land as nowhere else in the ocean. Seaweed often mantles the rock of the sea cliff between the levels of high and low tide, protecting it to some degree from the blows of waves. On the rock bench, each little pool left by the ebbing tide is an aquarium, abounding in the lowly forms of marine life. Below low tide level occur beds of molluscous shells, such as the oyster, with countless numbers of other humble organisms. Their harder parts, the shells of mollusks, the white framework of corals, the carapaces of crabs and other crustaceans, the shells of sea urchins, the bones and teeth of fishes, are gradually buried within the accumulating sheets of sediment, either whole, or far more often, broken into fragments by the waves. By means of these organic remains, each layer of beach deposits and those of the continental delta may contain a record of the life of the time when it was laid. Such a record has been made ever since living creatures with hard parts appeared on the globe. We shall find it sealed away in the stratified rocks of the continents, parts of ancient sea deposits now raised to form the dry land. Thus we have in the traces of living creatures found in the rocks, i.e. in fossils, a history of the progress of life upon the planet. Molluscous shell deposits. The forms of marine life of importance in rock making thrive best in clear water, where little sediment is being laid, and where at the same time the depth is not so great as to deprive them of needed light, heat, and of sufficient oxygen absorbed by seawater from the air. In such clear and comparatively shallow water there often grow countless myriads of animals, such as mollusks and corals, whose shells and skeletons of carbonate of lime gradually accumulate in beds of limestone. A shell limestone made of broken fragments cemented together is sometimes called coquina, a local term applied to such beds recently uplifted from the sea along the coast of Florida. Oolitic limestone, oon, an egg, lithos, a stone, is so named from the likeness of the tiny spherules which compose it to the roe of fish. Corals and shells have been pounded by the waves to calcareous sand, and each grain has been covered with successive concentric coatings of lime carbonate deposited about it from solution. The impalpable powder to which calcareous sand is ground by the waves settles at some distance from shore in deeper and quieter water as a limy silt, and it hardens into a dense, fine-grained limestone, in which perhaps no trace of fossil is found, to suggest the fact that it is of organic origin. From Florida Keys, there extends south to the trough of Florida Straits, a limestone bank covered by from 540 to 1,800 feet of water. The rocky bottom consists of limestone now slowly building from the accumulation of the remains of mollusks, small corals, sea urchins, worms with calcareous tubes, and lime-secreting seaweed which live upon its surface. Where sponges and other silica-secreting organisms abound on limestone banks, silica forms part of the accumulated deposit, either in its original condition, as for example the spicules of sponges, or gathered into concretions and layers of flint. Where considerable mud is being deposited along with carbonate of lime, there is in process of making a clayey limestone or a limey shale. Where considerable sand, a sandy limestone or limey sandstone. Consolidation of offshore deposits. We cannot doubt that all these loose sediments of the seafloor are being slowly consolidated to solid rock. They are soaked with water which carries in solution lime carbonate and other cementing substances. These cements are deposited between the fragments of shells and corals, the grains of sand and the particles of mud, binding them together into firm rock. Where sediments have accumulated to great thickness, the lower portions tend to consolidate under the weight of the overlying beds. Except in the case of limestones, recent sea deposits uplifted to form land are seldom so well cemented as are the older strata, which have long been acted upon by underground waters deep below the surface within the zone of cementation and have been exposed to view by great erosion. Ripple marks, sun cracks, etc. The pulse of waves and tidal currents agitates the loose material of offshore deposits, throwing it into fine parallel ridges called ripple marks. One may see this beautiful ribbing imprinted on beach sands, uncovered by their outgoing tide, and is also produced where the water is of considerable depth. While the tide is out, the surface of shore deposits may be marked by the footprints of birds and other animals, or by the raindrops of a passing shower. The mud of flats, thus exposed to the sun and dried, cracks in a characteristic way. Such markings may be covered over with a thin layer of sediment at the next flood tide, and sealed away as a lasting record of the manner and place in which the strata were laid. In Figure 150 we have an illustration of a very ancient, ripple-marked sand consolidated to hard stone, uplifted and set on edge by movements of the earth's crust, and exposed to open air after long erosion. Stratification. For the most part, the sheet of sea laid waste is hidden from our sight. Where its edge is exposed along the shore, we may see the surface markings which have just been noticed. Soundings also, and the observations made in shallow waters by divers, tell something of its surface. But to learn more of its structures, we must study those ancient sediments, which have been lifted from the sea and dissected by subaerial agencies. From them we ascertain that sea deposits are stratified. They lie in distinct layers which often differ from one another in thickness, in size of particles, and perhaps in color. They are parted by bedding planes, each of which represents either a change in material or a pause during which deposition ceased, and the material of one layer had time to settle and become somewhat consolidated before the material of the next was laid upon it. Stratification is thus due to intermittently acting forces, such as the agitation of the water during storms, the flow and ebb of the tide, and the shifting channels of tidal currents. Off the mouths of rivers, stratification is also caused by the coarser and more abundant material brought down at times of floods, being laid on the finer silt which is discharged during ordinary stages. How stratified deposits are built up is well illustrated in the flats which border estuaries, such as the Bay of Fundy. Each advance of the tide spreads a film of mud which dries and hardens in the air during low water before another film is laid upon it by the next incoming tidal flood. In this way the flats have been covered by a clay which splits into leaves as thin as sheets of paper. It is in fine materials such as clays and shells and limestones that the thinnest and most uniform layers, as well as those of widest extent, occur. On the other hand, coarse materials are commonly laid in thick beds, which soon thin out seaward and give place to deposits of finer stuff. In a general way, strata are laid in well-nigh horizontal sheets, for the surface on which they are laid is generally a very gentle inclination. Each stratum, however, is lenticular or lens-like in form, having an area where it is thickest and thinning out thence to its edges, where it is overlapped by a strata similar in shape. Crossbedding. There is an apparent exception to this rule where strata, whose upper and lower surfaces may be about horizontal, are made up of layers inclined at angles, which may be as high as the angle of repose. In this case, each stratum grew by the addition along its edge of successive layers of sediment, precisely as does a sandbar in a river, the sand being pushed continuously over the edge and coming to rest on a sloping surface. Shoals built by strong and shifting tidal currents often show successive strata in which the crossbedding is inclined in different directions. Thickness of sea deposits. Remembering the vast amount of material denuded from the land and deposited offshore, we should expect that with the lapse of time sea deposits would have grown to an enormous thickness. It is a suggestive fact that, as a rule, the profile of the ocean bed is that of a soup plate, a basin surrounded by a flaring rim. On the continental shelf, as the rim is called, the water is seldom more than 600 feet in depth at the outer edge, and shallows gradually towards shore. Along the eastern coast of the United States, the continental shelf is from 50 to 100 more miles in width. On the Pacific coast, it is much narrower. So far as it is due to upbuilding, a wide continental shelf, such as that at the Atlantic coast, implies a massive continental delta thousands of feet in thickness. The coastal plains of the Atlantic states may be regarded as the emerged inner margins of this shelf, and borings made along the coast probe it to the depth of as much as 3,000 feet, without finding the bottom of ancient offshore deposits. Continental shelves may also be due in part to submergence of the outer margin of a continental plateau, and to submarine abrasion. Deposition of sediments and subsidence. The stratified rocks of the land show in many places ancient sediments, which reach a thickness which is measured in miles, and which are yet the product of well-nigh continuous deposition. Such strata may prove by their fossils and by their composition and structure that they were all laid offshore in shallow water. We must infer that, during the vast length of time recorded by the enormous pile, the floor of the sea along the coast was slowly sinking, and that the trough was constantly being filled, foot by foot, as fast as it was depressed. Such gradual, quiet movements of the earth's crust not only modify the outline of coasts, as we have seen, but are of far greater geological importance in that they permit the making of immense deposits of stratified rock. A slow subsidence continued during the long time is recorded also in the succession of the various kinds of rock that come to be deposited in the same area. As the sea transgresses the land, i.e. encroaches upon it, any given part of the sea bottom is brought further and further from the shore. The basal conglomerate formed by boulder and pebble beaches comes to be covered with sheets of sand, and with these layers of mud as the sea becomes deeper and the shore more remote, while deposits of limestone are made when at last no waste is brought to the place from the now distant land, and the water is left for the growth of mollusks and other lime-secreting organisms. Rate of deposition. As deposition in the sea corresponds to denudation on the land, we are able to make a general estimate of the rate at which the former process is going on. Leaving out of account the soluble matter removed, the Mississippi is lowering its basin at the rate of 1 foot in 5,000 years, and we may assume this as the average rate at which the Earth's land surface of 57 million square miles is now being denuded by the removal of its mechanical waste. But sediments from the land are spread within a zone but 200 or 300 miles in width, along the margin of the continents, a line 100,000 miles long. As the area of deposition, about 25 million square miles, is about 1/2 the area of denudation, the average rate of deposition must be twice the average rate of denudation, i.e. about 1 foot in 2,500 years. If some deposits are made much more rapidly than this, others are made much more slowly. If they were laid no faster than the present average rate, the strata of ancient sea deposits exposed in a quarry 50 feet deep represent a lapse of at least 125,000 years, and those of a formation 500 feet thick require for their accumulation 1,250,000 years. The sedimentary record and the denudation cycle. We have seen that the successive stages in a cycle of denudation, such as that by which a landmass of lofty mountains is worn to low plains, are marked each by its own peculiar landforms, and that the forms of the earlier stages are more or less completely effaced as the cycle draws towards an end. Far more lasting records of each stage are left in the sedimentary deposits of the continental delta. Thus, in the use of such a land mass as we have mentioned, torrential streams flowing down the steep mountain sides deliver to the adjacent sea their heavy loads of coarse waste, and thick offshore deposits of sand and gravel record the high elevation of the bordering land. As the land is worn to lower levels, the amount and coarseness of the waste brought to the sea diminishes, until the sluggish streams carry only a fine silt, which settles on the ocean floor, near to land in white sheets of mud which harden into shale. At last, in the old age of the region, its lower plains contribute little to the sea, except the soluble elements of the rocks, and in the clear waters near the land, lime-secreting organisms flourish, and the remains accumulate in beds of limestone. When long-weathered lands mantled with deep, well-oxidized waste are uplifted by gradual movements of the earth's crust, and the mantle is rapidly stripped off by the revived streams, the uprise is recorded in white deposits of stream and yellow clays and sands upon the adjacent ocean floor. Where waste is brought in is more than the waves can easily distribute, as off the mouths of turbid rivers which drain highlands near the sea, deposits are little winnowed, and are laid in rapidly alternating shady sandstones and sandy shales. Where the highlands are of igneous rock, such as granite, and mechanical disintegration is going on more rapidly than chemical decay, these conditions are recorded in the nature of the deposits laid offshore. The waste swept in by streams contains much feldspar and other minerals, softer and more soluble in quartz, and where the waves have little opportunity to wear and winnow it, it comes to rest in beds of sandstone, in which grains of feldspar and other soft minerals are abundant. Such feldspathic sandstones are known as arcosi. On the other hand, where the water is supplied to the sea comes chiefly from wide, sandy coastal plains, there are deposited offshore clean sandstones of well-worn grains of quartz alone. In such coastal plains, the waste of the land is stored for ages. Again and again they are abandoned and invaded by the sea from time to time. The land slowly emerges and is again submerged. Their deposits are long exposed to the weather and sorted over by the streams, and winnowed and worked over again and again by the waves. In the course of long ages, such deposits thus become thoroughly sorted, and the grains of all minerals softer than quartz are ground to mud. Deep sea oozes and clays. Globigerina ooze. Beyond the reach of waste from the land, the bottom of the deep sea is carpeted, for the most part, with either chalky ooze or a fine red clay. The surface waters of warm seas swarm with minute and lowly animals belonging to the order of Foraminifera, which secrete shells of carbonate of lime. At death, these tiny white shells fall through the seawater like snowflakes in the air, and slowly dissolving seem to melt away before they can reach depths greater than about 3 miles. Near shore they reach bottom, but are masked by the rapid deposit of waste derived from the land. At intermediate depths, they mantle the ocean floor with a white, soft lime deposit, known as Globigerina ooze, from a genus of the foraminifera, which contributes largely to its formation. Red clay. Below depths of from 15 to 18,000 feet, the ocean bottom is sheeted with red or chocolate-colored clay. It is the insoluble residue of seashells, of the debris of submarine volcanic eruptions, of volcanic dust wafted by the winds, and of pieces of pumice drifted by ocean currents far from the volcanoes from which they were hurled. The red clay builds up with such inconceivable slowness that the teeth of sharks and hard ear bones of whales may be dredged in large numbers from their deep ocean bed, where they have laid unburied for thousands of years, and an appreciable part of the clay is also formed by the dust of meteorites consumed in the atmosphere, a dust which falls everywhere on sea and land, but which elsewhere is wholly masked by other deposits. The cold, dark abysses of the ocean are far less affected by change than any other portion of the surface of the lithosphere. These vast silent plains of ooze lie far below the reach of storms. They know no succession of summer and winter, or of night and day. A mantle of deep and quiet water protects them from the agents of erosion which continually attack, furrow, and destroy the surface of the land. While the land is the area of erosion, the sea is the area of deposition. The sheets of sediment which are slowly spread there tend to efface any inequalities and to form a smooth and featureless subaqueous plain. With few exceptions, the stratified rocks of the land are proved by their fossils and composition to have been laid in the sea. But in the same way they are proved to be offshore shallow water deposits, akin to those now making on continental shelves. Deep-sea deposits are absent from the rocks of the land, and we may therefore infer that the deep sea has never held sway where the continents now are, that the continents have ever been, as now, the elevated portions of the lithosphere, and that the deep seas of the present have ever been its most depressed portions. The reef-building corals. In warm seas, the most conspicuous of rock-making organisms are the corals known as the reef builders. Floating in a boat over a coral reef, as for example off the south coast of Florida or among the Bahamas, one looks down through clear water on thickets of branching coral shrubs, perhaps as much as 8 feet high and hemispherical masses 3 or 4 feet thick, all abloom with countless minute flower-like coral polyps, gorgeous in their colors of yellow, orange, green, and red. In structure, each tiny polyp is little more than a fleshy sac whose mouth is surrounded with petal-like tentacles or feelers. From the seawater, the polyps secrete calcium carbonate and build it up into the stony framework which supports their colonies. Boring mollusks, worms, and sponges perforate and honeycomb this framework, even while its surface is covered with myriads of living polyps. It is thus easily broken by the waves, and white fragments of coral trees strew the ground beneath. Brilliantly colored fishes live in these coral groves, and countless mollusks, sea urchins, and other forms of marine life make here their home. With the debris from all these sources, the reef is constantly built up until it rises to low tide level. Higher than this, the corals cannot grow, since they are killed by a few hours of exposure to the air. When the reef has risen to wave base, the waves abrade it on the windward side, and pile to leeward coral blocks torn from their foundation, filling the interstices with finer fragments. Thus they heap up along the reef low, narrow islands. Reef building is a comparatively rapid progress. It has been estimated that off Florida, a reef could be built up to the surface from a depth of 50 feet in about 1,500 years. Coral limestones. Limestones of various kinds are due to the reef builders. The reef rock is made of corals in place and broken fragments of all sizes, cemented together with calcium carbonate from solution by infiltrating waters. On the island beaches, coral sand is forming oolithic limestone, and the white coral mud with which the sea is milky for miles about the reef in times of storm settles in concrete into a compact limestone of finest grain. Corals have been among the most important limestone builders of the sea ever since they made their appearance in the early geological ages. The areas on which coral limestone is now forming are large. The Great Barrier Reef of Australia, which lies off the northeastern coast, is 1,250 miles long and has a width of from 10 to 90 miles. Most of the islands of the tropics are either skirted with coral reefs or themselves of coral formation. Conditions of coral growth. Reef-building corals cannot live except in clear salt water, less as a rule than 150 feet in depth, with a winter temperature not lower than 68 degrees Fahrenheit. An important condition also is an abundant food supply, and this is best secured in the path of the warm oceanic currents. Coral reefs may be grouped in three classes: fringing reefs, barrier reefs, and atolls. Fringing reefs. These take their name from the fact that they are attached as narrow fringes to the shore. An example is the reef which forms a selvage about a mile wide along the northeastern coast of Cuba. The outer margin, indicated by the line of white surf, where the corals are in vigorous growth, rises from about 40 feet of water. Between this and the shore lies a stretch of shoal across which one can wade at low water, composed of coral sand, with here and there a clump of growing coral. Barrier reefs. Reefs separated from the shore by a ship channel of quiet water, often several miles in width and sometimes as much as 300 feet in depth, are known as barrier reefs. The seaward face rises abruptly from the water too deep for coral growth. Low islands are cast up by the waves upon the reef, and inlets give place for the ebb and flow of the tides. Along the west coast of the island of New Caledonia, a barrier reef extends for 400 miles, and for a length of many leagues seldom approaches within 8 miles of the shore. Atolls. These are ring-shaped or irregular coral islands, or island-studded reefs enclosing a central lagoon. The narrow zone of land, like the rim of a great bowl sunk into the water's edge, rises hardly more than 20 feet at most above the sea, and is covered with a forest of trees such as the coconut, whose seeds can be drifted to it uninjured from long distances. The white beach of coral sand leads down to the growing reef, on whose outer margin the surf is constantly breaking. The steep face of the reef falls off abruptly, often to depths of thousands of feet, while the lagoon varies in depth from a few feet to 150 or 200, and exceptionally measures as much as 350 feet. Theories of coral reefs. Fringing reefs require no explanation, since the depth of water about them is no greater than that at which coral can grow. But barrier reefs and atolls, which may rise from depths too great for coral growth, demand a theory of their origin. Darwin's theory holds that barrier reefs and atolls are formed from fringing reefs by subsidence. The rate of sinking cannot be greater than that of the upbuilding of the reef, since otherwise the corals would be carried below their depth and drowned. The process is illustrated in Figure 161, where V represents a volcanic island in mid-ocean, undergoing a slow depression, and SS the sea level before the sinking began, when the island was surrounded by a fringing reef. As the island slowly sinks, the reef builds up with equal pace. It rears its seaward face more steep than the island slope, and thus the intervening space between the sinking, narrowing land and the outer margin of the reef constantly widens. In this intervening space, the corals are more or less smothered with silt from the outer reef and from the land, and also deprived in large measure of the needful supply of food and oxygen by the vigorous growth of the corals on the outer rim. The outer rim thus becomes a barrier reef, and the inner belt of retarded growth is deepened by subsidence to a ship channel, SS representing sea level at this time. The final stage where the island has been carried completely beneath the sea and overgrown by contracting reef, whose outer ring now forms an atoll, is represented by S2S2. In very many instances, however, atolls and barrier reefs may be explained without subsidence. Thus, a barrier reef may be formed by the seaward growth of a fringing reef upon the talus of its sea face. In Figure 162, F is a fringing reef, whose outer wall rises from about 150 feet to the lower limit of the reef-building species. At the foot of this submarine cliff, a talus of fallen blocks, T, accumulates, and as it reaches the zone of coral growth, becomes the foundation on which the reef is steadily extended seaward. As the reef widens, the polyps of the circumference flourish, while those of the inner belt are retarded in their growth and at last perish. The coral rock of the inner belt is now dissolved by seawater and scoured out by tidal currents until it gives place to a gradually deepening ship channel, while the outer margin is left as a barrier reef. And I think I'm going to leave it there before we get to the explanation of atolls. As always, if you'd like to pick up where I'm leaving off, you can find the original on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night, and sweet dreams.